Okay, so today's session is about simple FEA analysis principles and how to get started with simple linear static analysis. So to give you an overview of today's webinar, we'll talk about CA overview, finite element analysis procedure, and then I'll give you some basis about linear static analysis, and finally a very simple demonstration example to see how it works. Okay, so first of all, computer-aided engineering, so this is CAE. So it means that, CAE is any way that you can use to evaluate the performance of a model which is created by CAD within a computer and revise the model based on simulation data. So the CAE introduction in the market has a lot of effects because it helps to predict the performance of characteristics of products prior to the test production, and it also helps to shorten the development period and reduce the processing costs. So when you talk about CAE, the first thing you have to think is that it's a numerical analysis method. So when you have an actual phenomenon, you have to actually model it mathematically. So you can use some expressions of maths. Then you have to think about the behavior, the shape, and which represent the boundary and initial condition. And when you have this mathematical model, you can run the analysis, and this gives you the numerical analysis. So this kind of CAE analysis is used in all industries. So automotive, heavy equipment, semiconductor and displays, aviation, aeronautics, space, communication device, shipbuilding, medical device, energy, consumer goods, and electrical or electronic equipment. So you can see that such software is very wide and it can provide a lot of information and to all kinds of industries. Okay, now I'll review a few slides about the finite element method because it's very important to understand how it works before really entering into the details about linear static. So first of all, as you know, you have solid mechanics, which describes the behavior of the solids. The thing is that solid mechanics can be applied to very simple shapes, and for these shapes you can obtain a very precise solution. But unfortunately, this is not the case if you have a very complex shape. So if you look at the scheme here, you have this kind of simple analysis model, then it gives you a mathematical model that you can represent with a differential equation, which incorporates some boundary and initial conditions as well. And then you can either get a precise solution or you can get an approximate solution. So the approximate solution is using some linear algebraic equation resolution, and this can be the finite element method. So what is actually called the finite element method? So finite element method represents a method which is used to discretize a physical model. So when you have a real model like this one, let's say you cannot determine the total area, and it's difficult to apply some load on this. So the basic method, which is the main principle of the finite element method, is just to divide this surface in very small surfaces, which are called elements, and at the boundary of these elements you have some nodes. So once you get this finite element model, you are able to solve the equation on each of these small triangles. So the basic equation which is used can be defined like that. So here I'm talking about linear type of equation, but this is what we'll talk about today anyway. So you have a matrix which is called the stiffness matrix, multiplied by the displacement vector is equal to the force of the vector. So this equation is valid because this is a linear system. So if you're doing stress analysis, the K matrix will be equal to the stiffness, the delta will be displacement, and the F will be the force. But if you're doing a temperature analysis, the K will be the conduction matrix, the delta will be temperature, and the F will be the heat flux. So basically, to explain very simply what you get, is that basically you know the K matrix from the material data. The F is given from the boundary condition that you apply to the model. So the only thing which is done is to inverse this matrix and to get the displacement through the finite element method, linear static method, I mean. So to give you a simple flow chart, you have the first model, which is a continuum mechanic model. This first step is to discretize this model into small elements, and then you'll have to define the boundary condition on the model and the loads. And then the governing equation will be solved for each element. So on each of the small particles of the model, this matrix equation will be solved, inversed, and then it will be combined together again to give you the final total solution. So this is the basic. So it's very simple to understand. It's simply to cut something in very small parts and to apply the equation to each part and then to combine everything again. The thing is that you have, so the example I gave you is a 2D plate element, but you may have several types of elements in function of the needs. So, for example, you have 1D element like rod and truss, which are represented by just 1D segments. You have 2D elements like shell, plane stress, plane strain, or axisymmetric, which are represented by area. And you have 3D models, which are actually volumes, like that. So if you have a 1D element, you must give the software the area, which will be constant to this beam. So actually, you know that your model is always in 3 dimensions, but the 3 dimension will be created from 1 dimension, which will be free, and 2 dimension will be fixed due to the area of the cross-section, which is fixed. For 2D, you have 2 degrees of freedom and 1 degree, which is the thickness of the plate, which is fixed. And for 3D, the 3 degrees of freedom are available. Now you have to make the distinction between lower order and high order elements. So first order are elements which just some nodes at the boundary. So you have basically 2 types, the triangle and the quad elements. So the triangle has 3 nodes, the quad has 4 nodes, and the approximation on these elements is totally linear. In the case of second order elements, called also higher order elements, you have a mid node which is added in the middle, and it causes the fact that you have now a second order interpolation function which is used on your element. So it will be more precise and your results will be more accurate if you use second order elements. Now let's explain you in which situation you need to use 1D element. So 1D elements, so basically bar and beams elements, are defined by 1 line element and 2 end nodes, and they are usually used when a member is too long compared to the measurement of the cross section. So when it is under bending deformation. So these are the properties that can be assigned to this, so I will not really detail that. The 2D elements, like the shell elements, are often used when you have very thin sheet structures and when they are under bending deformation. So it helps you to consider 2D stress conditions like bending and shear deformation. So you can imagine the silos in a plant construction, which is basically the perfect shape to use such 2D elements. And the same, you have some different type of properties. So the properties, it depends on the type of things you want to do. So plate elements are a special type of shell. So the curvature of the plate is 0, but the curvature of the shell can be different from 0. The application, like I told, soda cans, wing of airplane, roof of Olympic Stadium, such application can be used with 2D plate elements, for example, or shells. Now 3D elements, so solid elements, which are the most used in practice because they can really represent the real behavior of the model. The disadvantage about 3D elements is that they increase a lot the computation of your computer, so you need to have a good computer if you have a big model. Now you have different types of 3D elements. You can think about tetrahedron, pentahedron, hexahedron, and all that can be combined together using, for example, hybrid meshing, which is automatic in midas and NFX. Now I'll talk very briefly about several types of analysis that you can consider when you're doing finite element analysis. So today we will center about linear static, but I'd like just to talk a bit about different types of analysis which is possible, so you know what is possible and you can eventually have some more documentation about all that later on. So first of all, linear static, so it will be the topic of today. I'll talk a bit more in detail a bit after. So this is basically to examine the deformation of a structure under an external load. So it's applied for cases in which the material is in the elastic region. So when the material stays within the Hooke's law, and when you can consider infinitesimal deformation and static load. So basically, the type of analysis we use the most often is linear static, because this is the most simple type of analysis. Now, model analysis examines the natural frequency of the structure and graphs the mode shape of each natural frequency in order to analyze the resonance of the model. So you can see for this car model, for example, we'd like to know what is the resonance of the bending. So if you test the model analysis for these different frequencies, you'll see that different mode shape will be shown. So in this case, you'll have first from bending mode, here you have weird torsion mode. So this is the model. Buckling analysis is a bit special type of analysis, which consider the fact when you have a compression force load which is applied to the model, and the model is actually has a thickness which is very thin, for example. So what happens is that you apply the load on the top, and theoretically it shouldn't fail, because the material, if you do exactly the equation and everything, it shouldn't fail. But due to the very thin shape of the model, you have some kind of uncertainty, some kind of discontinuity in your analysis, which causes the model to deform. So this is important to understand what is the buckling load, because the buckling load will cause the model to fail much before the yield value. So this is why it's important to calculate buckling. Now you have also nonlinear static analysis. So nonlinear static is when you cannot just say that your model is linear, because, for example, you have large deformation, or you want to use a nonlinear elastoplastic material, for example, to consider plastic deformation, or maybe you have general contact. So in these cases, you need to use nonlinear static. So you have a few examples here, like this boost. So you see the deformation is very large. So it's, of course, it doesn't fit to the linear type of analysis. Heat transfer analysis. So heat transfer is when the temperature changes. So you have a heat flow due to the temperature difference and distribution and the change in temperature. So it's very useful to optimize the design of electronic products, for example. So in this case, you have the existing design, and this is an improved design with a heat sink to cool the model. So at the first step, it was 310 degrees Celsius, and you see after the simulation of heat transfer analysis, it has been improved to a maximum temperature of 132 degrees Celsius. So this is very useful. Thermal stress is when you want to investigate the thermal deformation, so due to the temperature in your model. So it can be done in several manners, and you have all that available in NFX as well. Now you have linear dynamic type of analysis. So in this case, it's when you have a transient response, for example. So you have some part which is moving with the time, and you want to know what is the deformation following the time on your part. You can be also a response to a frequency response. So you have an oscillation in the frequency domain, and then you want to see where is actually the resonance. So for which frequency of oscillation you'll get a resonance. So it's also very important. And very complex type of analysis, but very interesting as well, explicit nonlinear dynamic. So it's actually a combination of dynamic and nonlinear type of analysis. So you have explicit, but you have also implicit, and it's basically used for very short time events, like the crash of a hard drive almost on the ground, for example, like in this case. Fatigue analysis is used to predict the fatigue life of an object under a repeated load. So maybe if the load is only applied once, it will not destroy your model, but if it is applied for several years, you'll see the effect of fatigue in the model. So usually all engineers need to take account of that. Composite material. So in the case of your material using composites, you can also consider that using the ply layups inside the software. Topology optimization. So this is a specific type of analysis mostly for designers who want to optimize the shape of their model of the part. So the software is actually giving you some recommendation about the best optimize the shape for the model. And you have flow analysis also, CFD. So this is a very large domain as well that I already discussed previously in several webinars. So now let's just talk briefly about some advantage and disadvantage of the finite element analysis. The major advantage is that there's no restriction on the geometric shape, so on the load and the boundary conditions. So you can really have a model which is very close to the reality, and you can analyze very complex problems that cannot be solved theoretically. Then you have the possibility to analyze in the continuum a very number of composites. You have the possibility to analyze nonlinear events, nonlinear material behavior, and it can be used in a lot of areas of engineering to assess the stress, the buckling, the vibration, the heat, the flow, all that we just talked previously. Now the disadvantage is that it's actually relatively easy for a beginner to use the software, but to evaluate the real reliability of the results, it requires a lot of experience. More of that, if you have a very general model, it's difficult to get the local stress analysis, and it requires a great amount of experience and knowledge to idealize and actually structure into a finite element model. So for large structure, it's greatly affected by the performance of the computer, so you need also a very good computer if you have a large model. So these are disadvantages. Now, let's talk briefly about some misunderstanding about FEA analysis. That some people think about that, but it's not totally true. So first of all, is the mesh creation means everything for analysis? So of course, mesh is one of the input data, and it's required to perform the analysis, but the accuracy of the result is affected also by the boundary condition, the material properties, the fidelity of the actual shape and the components. The mesh creation is important and the quality is important, but it's not everything. It's only one part of what will give you the accuracy of the results. Can actually finite element analysis fully replace the structural and material testing? So it's something that a lot of you are wondering. So actually in the initial stage of a new problem, a new design, the number of structural and material testing will increase and are still required because it's a new analysis process and it must be confirmed. So you cannot be sure that the simulation will give you the expected result if you don't have a result from simulation to compare with it. So it's important to do some testing, and once the process is well defined, then the finite element will give you a very huge potential, and also you have to spend a bit much less money on the actual real testing. Finite element is easy, not difficult. So many designers underestimate the difficulty of the modeling and the complex change of the result based on the input value. And they come very quickly with conclusion to determine the design, but this actually requires a lot of experience, like I told. So in order to correctly understand the meaning of the result and verify the accuracy, there must be understanding of the meaning of the various parameters and the method to perform the finite element analysis. Moreover, obtaining the analysis result is only half of the process, but the analysis results can be properly analyzed so you need to have a very good analysis of the result in order to be sure that the physical phenomena that are described are corresponding to the assumptions you made and the result you got. Learning the interface is the same as learning finite element analysis. Well, some people tend to think that if they can use a software or they can use an analysis program, it's almost the same than using finite element analysis, but actually it requires a great amount of experience to actually be able to reflect the real knowledge of the design to understand and analyze the results well. Now let's talk about finite element analysis procedure. So I'll talk about three things: the typical procedure, the CAD data revisions, and the three tasks that the typical designers consider difficult. So first of all, this is the typical process. So first of all, the product design is done in CAD. Then the revision which are needed of the CAD need to be done before doing the CA analysis. And this is typically something that the designer overlook. So they took directly the CAD model and they think they can run the simulation directly on that. But it requires some experience actually to simplify the model. Then the second step is transferring the CAD data to CAE product and divide the mesh based on the model shape and then do the setting of the load and boundary condition and analysis condition. So this is what is called the pre-processing. Then performing the calculation, this is the real analysis. So it's in this step that the solver is really acting. Then processing the result is called the post-process. And then the final step, and maybe the most important, analyzing and judging the results. So these three steps are basically the typical thing that the designer think is difficult. So we'll see why. So first of all, the task that designer overlook, it's the simplification of the CAD model. So it happens a lot that in your CAD model, you have a lot of small fillets and small holes that actually are not required for the simulation. So it will give you almost the same result with this or without, but it will make a big difference because these small fillets and holes will cause the fact that you need to increase the mesh size around this and make a very, very small mesh around this shape if you want to get correct result. So it's much better to simplify all that when it's not needed and to prepare the model correctly for the CAE analysis. And here are the three tasks that the typical designers consider difficult. The first one is the mesh division based on the model shape. So the proper mesh size is very important, but it's difficult to actually assess what is the correct size, and the designer has not experience on that, so they usually either took a size which is too large or a size which is too small. So in function of that, the error that you'll get will significantly affect the analysis results. Now the setting of the load and boundary condition is important, and it needs to be set as close as possible to the actual phenomenon, and I'll set by considering a symmetry, for example, because symmetry will help you to divide a lot the number of elements in your model, so it's very important as well. And analysis condition need to consider the behavior of the model, so especially when you have large deformation and geometrical non-linearity. Now the third thing is the interpretation of the result, which is very important. It's necessary to check the result with the simulation, the real test data. And what you should think also that for most stresses you use the formula stress, but for some type of material like brittle materials, the maximum principal stress must be checked. So this is one problem that happens sometimes. And also you should be careful about what type of analysis you're doing. Sometimes you're doing linear static because it's more simple, but you'll have a huge difference if you do linear static or non-linear static. So you can see here when you have geometric nonlinearity, which is considered, and it can actually calculate accurately the amount of deflection. So you see the shape is quite different between two models. Now finally, let's talk about linear static analysis. So linear static means, so it was the most, let's say, most used because this is really the foundation and the start of all analysis. And examines the deformation of the structure under an external load, and it helps you to get the strength stability. So a very simple thing to remind what is this linear static analysis is just to separate into two things. On one side you have linear and you have static. So linear means that the relation between the load to the applied object and the response is linear. So for one small force that you apply, the displacement will be proportional. So if your force increases, the displacement will be increased proportionally. So this is linear. So it uses the Hooke's law to calculate the material behavior, and the deformation must be small, so this is a requirement, so you should always check that your deformation will be small, and the boundary condition must not change. So when the load is applied to the structure, it stays at the same position, and the orientation of the load also stays the same during the analysis. Now the second part, static analysis. So static means that the applied load does not vary based on the time. So it is independent of the time. So it ignores the inertial and damping forces, and the purpose of the static analysis are to avoid the failure by preventing the stress concentration, and to retain a uniform stress distribution by eliminating unnecessary parts and further strengthening necessary parts in order to produce the optimum design. So what it means is that linear static is basically just to check if your model is strong enough, so if it's not going into the plastic area, so you'll check the safety factor of all the areas of the model, and if your safety factor stays over 1, it means that your model is still in the linear domain. Then when you have that, you can check where is the stress concentration and improve your model consequently in function of that. So you can see if your design is good or bad and improve your design. So if you want to get more learning resources, you can go on our website. Well, you will find some tutorials. So here you have different tutorials. You can also join the next webinar that will be by clicking on the Try Learning. So the next webinar will be next month and will be about the material nonlinearity modeling for the engineering. And you can go on the website to join this webinar, so you're invited if you're interested by this topic. Now, if you want to download the NFX trial for 30 days, you can request a fully functional trial for 30 days directly on the website, and you will receive this trial. And okay, so this is the end, and now we'll have a Q&A session so you can ask your questions. So if you have some questions, please ask them in the question section. Okay, I have a question about the special mass. Okay, so you can as well, you don't have to do that automatically, apply automatically the hydrostatic mass to all the nodes. You can do it also directly in the properties of the mesh on the plates. You can add this additional mass to the element. And you can as well create it on all the nodes if you want or if you need to do that. So you have the choice. Okay, I have other questions. Can we receive the slides of this webinar? Yes, you can receive. After the webinar, I will send the recording and the PPT, so you can check it after the session. Is there any more question about this webinar? Okay, then I think it's all for this session. I thank you very much for joining the webinar, and I hope you'll have some interest about finite element analysis and about the software. And if you have any question at any time, you can send it to my email. So my email is cyprian@midasit.com. I will write it here. So you can send me anytime your question, and I will answer as soon as possible. Yes, see you next month for the next webinar. Goodbye.